today we are going to talk about diffusion. What is diffusion? Diffusion is basically at microscopic level, it is random thermal motion of carriers. So, if you look at microscopic level, it is random thermal motion of carriers. And if you recall, we discussed this when we started discussing about drift of carriers, and we said that in the classical picture, if we look at the thermal motion of carriers, then they are always moving around, but their net motion is 0. So, this random motion of the carriers is what leads to diffusion. But earlier we said that if we have this motion, then we do not have any effective transport of carriers. So, what is happening? If basically what we are saying is, if we have a semiconductor, and in this semiconductor, if I divide it by, let us say, this material in different sections, just to illustrate, and I am going to look at only motion in one dimension, although we know that charged particles are going to move in any random direction, but it makes it easier to show what we want to display here. Let us look at behavior of electrons in this material. So, there are electrons in different sections. The material is homogeneously doped. So, we have sort of homogeneous concentration of electrons in these uniform sections that I have drawn of the material. And at any point, what we are saying is that due to random motion, these particles are always moving around. So, at any given point, if the motion is completely random, there is half a probability that it will go in the plus x direction and half probability that it will go in the minus x direction, which means I can represent it in this manner. Now, this is going to be true for all other layers, which means I am going to have this interaction between particles in different sections, but as you can see, overall this will not lead to any change, because my concentration is homogeneous, which means that the number of particles that I am taking out from a given section is equal to the number of charge carriers which are coming in that section. So, because of this thermal motion, if concentration is uniform, for charge carriers, and when will that be? It will be when you have uniform doping of the semiconductor. Then due to diffusion, due to this thermal random motion, you have no change or transportation of carrier. So, when does it become important? So, diffusion become important when we have non-homogeneous carrier concentration in the material or in the device structure, which could be a heterostructure or a multi-layer. So, why is that possible? Because we have seen that it is possible for us, and when we will look at the devices, that we can make a material such that the concentration of, let us say, donors at point x is equal to 0 may be at some value, while the concentration of donors at point L, x is equal to L, is not the same. We can always process the material such that these two are not the same. You may wonder how that is possible. It is possible because when we try to dope a material, normally what we do is we start with a uniformly doped intrinsic material of length L, and then we are going to start diffusion from one end, which basically means that the material will always have a different concentration at this end versus at the opposite end. And hence, in the processing of semiconductor, it is very common to have non-uniform concentration gradient in the material, and hence the diffusion becomes an important process. There can be other situation when we often make devices, we put two different kind of materials adjacent to each other, which means I may be having a p-n junction where I put in close contact metallurgical contact a p junction, a p semiconductor and a n semiconductor, let us say p silicon and n silicon, and for obvious reason it is clear that the carrier concentration of hole here is going to be very different from here, and vice versa carrier concentration of electrons here is going to be very different from n to p. So, there are several situations which we will deal with later also in the lectures, where you have a concentration gradient in the device structure or in the material that would lead to diffusion. So, what will happen in that case? If you do have a concentration gradient, you can one can visualize this process of diffusion in the manner that those same sections that I have drawn earlier have now different carrier concentration. I can also plot it in terms of a graph, where I will let us take an example of a donor. So, carrier electron concentration versus x, and let us say there are more electrons, this is being represented by electrons, there are more electrons here, and as we go on the number of electrons is getting reduced or doping concentration is getting reduced, and so on and so forth. So, if I have to represent this on this axis is going to be the intrinsic electron carrier concentration and some value and a change in the carrier concentration. Now, in this situation if we look at the same random motion of carriers, you can see that the number of carriers are more here, hence the number coming to the right is going to be more. On the other hand, the number going to the left, which is going to this section, is going to be less. As a result, there is going to be a change in electron concentration here. Vice versa, or in the same way one can see same thing will happen to each section as we go along, because the the number of electrons leaving a particular section is not going to be always same as number of electrons coming to that section, except for some special case. So, in general we assume it is not going to be same. In that situation, eventually with time one would expect that this variation in carrier concentration should become less and less. So, with time, because of this diffusion process of random motion of carriers, one would expect the carrier concentration to become uniform if we have time to wait up till infinity. So, this is the reason for diffusion process, and we have this in most materials, because you have a situation in which the device structures or material itself have a non-uniform carrier concentration. Now, in this particular case, since the carriers are charged, diffusion also leads to a current. So, diffusion of carriers, because they are charged, diffusion will give rise to a diffusion current. And this will be of two kind, one due to electrons and the other due to holes. And by the same token, whenever such a diffusion is taking place, you are going to have a charge accumulation in the material, and that will lead to some sort of a built-in field in the material that will oppose this diffusion process. So, the two go hand in hand. Whenever you have diffusion taking place, you will have some charge accumulation in the material, leading to electric field inside the material. So, diffusion in that sense is extremely important for semiconductor devices. Now, let us look at it, how do we deal with this process, or how would we account for it mathematically. So, what is the mathematical model for diffusion current? Now, in order to do this modeling, we are going to make certain assumptions to simplify it and simplify the analysis here. So, in general, the material has all 3 dimensions, and we will make sure that if you have concentration gradient, we take an example where the concentration gradient is only in one direction. So, it makes the problem one dimensional, which means if the material is having 3 dimensions, it is a semiconducting material, then it is only along the x direction we are having a concentration gradient. In the y direction and in the z direction of the semiconducting material, we have uniform doping, which means that the diffusion process does not lead to any change in the concentration in y and z direction. It is only the x direction that is important for us. So, let us do the analysis for this particular case for one dimensional diffusion. We also assume that there is a random probability of motion, which means in the x direction at any particular point, if we take any particular point in x direction, then number of particles moving in the right direction and number of particles moving in the left direction is exactly same at any point because of this random probability of motion. So, in other words, this means that the number of particles, in this case let us make this problem more specific, let us make this a problem for holes. So, particles are holes here, number of particles moving in positive and negative direction is exactly equal. We further simplify the problem, because if the motion of holes in the semiconductor is completely random, then they are all moving with a certain velocity distribution, all the holes are moving with certain velocity distribution, and in order to simplify the problem, we will say that all holes are moving with the average velocity of V bar. This simplifies the problem that we take all the particles have the same average velocity V bar, which is going to be equivalent to the thermal in the classical picture, the thermal velocity of the particles. Finally, we in order to simplify the analysis, we also make the assumption that all particles move at the same times. So, all holes move at the same time, and a fixed distance L, where L is given by the V bar T, and T is average time between scattering events. So, we have simplified the problem quite a bit by making these assumptions, and with that we can now find a formalism for finding out what would be the diffusion current in a semiconductor. So, let me take an example of in this particular case of a semiconductor. Let us say the whole concentration is represented by this curve, and I am looking at any particular point, and for simplicity let me say I am looking at x is equal to 0, and what we are saying here is that there is a mean free path for carriers which is L, for all holes, and L is this mean free path is given by the average velocity times the t the time between the scattering events. So, which means that if all carriers are starting to move at the same time, a hole which is here would have moved across this boundary in that time t, something which is here would have also come across this boundary in time t, and in this direction, and by the same token the carriers would have moved across the boundary in the opposite direction as well. So, now let us start looking at what is happening, how the carriers are moving across this boundary at x is equal to 0. So, if we look at that, then at x is equal to 0, let me just read out this quickly. To we are looking at the movement of carriers across the x is equal to 0 from the length on both sides equivalent to mean free path length, because this means that all the carriers which are in this volume would have crossed, half of them would have crossed to the left, and the carriers which are in the other volume would have also, half of them would have crossed to the right of this x is equal to 0 boundary, and this is representing my whole concentration in the semiconductor. So, then at x is equal to 0, the number of holes moving towards right is going to be, this is number of holes moving towards right, and crossing x is equal to 0 will be given by the we have to take the area of the semiconductor, area multiplied by this dimension, which is the number of holes in this particular dimension, which is basically given by the whole concentration times dx, this the length and the area, and it has to be integrated from minus L to 0, and since we said only half will move to right, because the other half are going to move towards left, this has to be divided by 2. So, this is the total number of holes moving from this volume and crossing x is equal to 0 in time t, where t is being defined by length divided by the average velocity, the mean free path divided by the average velocity. Similarly, I can write the number of holes moving in the left direction and crossing x is equal to 0 is going to be then given by a by 2 integrating over 0 to L dx. So, now we need to find out what was the total number of what is the net exchange of carriers across x is equal to 0. So, the net exchange of carriers across x is equal to 0 is going to be p minus p in the opposite direction. So, this is what I need to evaluate. Now, in order to evaluate this, I know that the mean free path L is small. The mean free path of carriers in a semiconductor which are moving around because of thermal motion is fairly small. If you recall, in the earlier lectures, you calculated that in order to prove the Drude theory, that this turns out to be close to the interatomic distance in the material, and so it is a fairly small number, and hence I can make some approximation for P of x, and I can take the Taylor series and limit the expansion to the first few terms. So, then I can write the carrier concentration of hole as carrier concentration of hole at point 0 plus the gradient of carrier concentration at 0 plus the other terms, and I am only going to use these for the integration purpose. So, using this expression and then putting it in the first two integration, I can find out what is the value of P going towards right and going towards left. So, P going in the right direction is substituting P of x is going to be given by negative of for negative of L the integration plus for the second part this is going to be a by 2 the value at 0 times L square divided by 2. So, this would be the value at minus L to the 0 to the value of 0. Similarly, I can write for the carriers moving in the other direction, that will be given by a by 2 P of 0 L plus a by 2 dP of dx at 0 L square by 2. So, now let us evaluate the difference of this to figure out what is the net carrier concentration across S is equal to 0, and we are finally interested in the flux of holes crossing x is equal to 0, and that will be given by P and this expression is coming out to be equal to at x is equal to 0 L square by 2. And since we are looking at the flux, we should divide this by the area multiplied by the time that it takes. So, if I divide this by the area and multiplied by the time, then we are looking at expression which is L square by 2 t dP dx at x is equal to 0, and L by t is nothing but V bar. So, this expression is nothing but V bar L by 2 dP dx 0. So, this is the flux of holes crossing x is equal to 0. This is the total value. The sign here is negative. Why is the sign negative? Because we have taken the positive x direction to be in this direction. This is the positive x direction, and carrier concentration is like this, which means the carriers are moving opposite to the positive x direction, and that is why this flux is negative. So, holes are moving in this direction, and that is why the negative sign comes here. and if this is a flux, we define a quantity called diffusion constant for holes, which is a material property. So, this is the diffusion coefficient for holes. Now, if holes are moving in this direction, which means there is a current due to that, and this current is going to be equal to, due to diffusion, is going to be the charge multiplied by the flux So, this would be then charge per centimeter square per second, which is the current multiplied by the area A. And if I want to represent it in terms of current density, then the whole current density due to diffusion will be given by Q, negative sign missing here, Q dP diffusion coefficient dx at x is equal to 0. So, this is the expression we wanted. We wanted to figure out due to diffusion in a semiconductor what would be the net motion of carriers, which would lead to a diffusion current over here. Now, there is a little bit more generalization which is required. I took this example for looking at the motion of carriers at boundary x is equal to 0, which was mainly for convenience. I could have taken x is equal to some value of x 1 and still I would get the same expression. So, this choice of x is equal to 0 was mainly to keep the math simple. Hence, in general term I would write this equation as the diffusion current will be given by the diffusion constant for holes dP dx, and at any x I evaluate, this will be giving me the diffusion current due to holes. So, this would be diffusion current due to holes. In the same manner, one can write, one can do a similar analysis and find that diffusion current due to electrons, and here there is going to be a change because this is now going to be positive. Why? It is going to be positive because conventionally the current is the in the opposite direction to the motion of electrons, and the diffusion current due to electrons will be given by this expression. Now, in this derivation we made the assumption of having only a motion of random motion of carriers in one dimension. If one does a more exact modeling and assumes that the carriers can move in all three directions, then the diffusion constant that we got here, the diffusion constant here has whether n or p has a value of V bar L divided by 2. This is for a one dimensional problem, but if I do it for a exact 3-dimensional problem, then this would be and be given by V bar L by 3 for a problem where the motion in all 3 dimension is considered, then it gets changed by 3. So, it is not very important what exact expression this is, because eventually we will be dealing with the diffusion coefficient here, which we will calculate from experimental values. So, for purpose of illustration, this one dimensional problem is much more easier to visualize where does the diffusion current come from. Keep in mind this V bar L, although I have written for electron and holes, will be different for electron and holes, and the reason for that is because electrons are moving in the conduction band and holes are moving in the valence band, and so they will have a their thermal motion is going to be dictated by the band structure of their particular band, and hence you will have different values of V bar for electron and holes. It will not, it is not going to be the same value. Now, having come up with an expression for diffusion current, what is important is what is this diffusion coefficient N or P. When we were talking about drift, we looked at the carrier motion in response to the electric field, and then the parameter which is important in case of drift is the mobility of carriers. And then we looked at what is the behavior of this mobility as a function of maybe doping concentration of semiconductor or as a function of the temperature. So, we will like to do the same thing for the diffusion constant. So, but before we do that, it becomes easier if we see the relationship between the carrier motion due to diffusion and the carrier motion due to drift. Both come from a similar reason, and we can find this relationship and then study what is the nature of this diffusion constant. So, in order to illustrate the relationship between diffusion coefficient and the mobility of carriers, we first develop a famous relationship of Einstein relationship. And in this to derive this, let us take an example where we take a semiconductor and let me take a n type semiconductor having a donor concentration which is something like this. And if we have a donor concentration like this, so basically this is non-uniform doping. And if we have non-uniform doping, which means in equilibrium, the first condition that we must have in this material, that in equilibrium the Fermi level EF is constant or dEF dx is 0. So, in equilibrium we have the Fermi level which is constant. Now, if Fermi level is constant and I have a doping concentration which is changing in the x direction, which means I must have higher concentration of carriers here and lower concentration of carriers here, which basically means that in this particular material I have some amount of band bending of the semiconductor. Conduction band, valence band. If I do that, basically what I am saying is at this point there are more electrons and at this point there will be less number of electrons because of the non-uniformity of doping. EF will remain same, EC and EV will band in order to accommodate this doping concentration, and EI will also be shown in this manner, that is the intrinsic level. So, so the first assumption here is that in equilibrium, if there is nothing else, no other applied field, the Fermi level is constant in the material. The second thing is, because this Fermi level is constant, you must have band bending. Band bending is essential to accommodate the non-uniformity, and if you have band bending, which means you have a non-zero electrical field is established in the material. So, in this situation, then we look at what is happening in the material. Since the material is in equilibrium, this means that the drift current is equal to the diffusion current, or what I will find in this material is the J electron for electron current due to drift plus J n due to diffusion is going to be 0. Now, what is this J n? So, at any point x, at any point in the material, keeping the analysis one dimensional, I have basically the drift current, which is charge multiplied by the mobility of the electrons, concentration of electrons at that point times the electric field, plus the diffusion current, which is charge multiplied by the diffusion coefficient of electrons and the gradient of electrons at that point. This is going to be the two values for electrons. This should be equal to 0. Now we lead this to the final solution and relationship between the mobility and diffusion constant in equilibrium. And so we take help of one additional assumption, which says that let us solve this for non-degenerate semiconductors. And in that case, I have an expression for n, which can be written in terms of the band energy So, I know what n is at any particular point, and then if I know n, I can calculate d n dx. I also know from the discussion during drift that the field inside the semiconductor can be related to the band bending due to this field by the expression 1 over q and the band bending due to as a result of this field inside the semiconductor. So, if I use these expressions for a non-degenerate semiconductor, I can write the electric field can be given as the amount of band bending dn, and dn of dx will be nothing but n time dEc dx. So, if we simplify this expression, this basically generates that mobility, this cancels out and cancels out, and dEc dCx cancels out. So, mobility divided by the diffusion constant is going to be sorry, when I differentiate this, I will get expression of 1 over kT is going to be given by negative q over kT. Now, this is very interesting. What it is saying is that the carrier mobility divided by the carrier diffusion coefficient ratio, this ratio is a constant. It only depends on the charge of the carrier, which is electron charge, Boltzmann constant, and the temperature. And this then immediately says that if I know my mobility of carrier, I can calculate what is the diffusion coefficient for that carrier. And let me take an example here. So, in the earlier lectures, we have taken example for, let us say, the mobility of electrons is 1360 centimeter square per volt second, which would mean that at room temperature, this is going to be, if I want to calculate diffusion constant, it will be mu n divided by q over kT, and this kT over q is like voltage, and if I am calculating at room temperature, kT over q is given by 0.026 volts. So, this gives me the diffusion coefficient will be 1360 centimeter square per volt second multiplied by 0.026 volts, and this comes out to be equal to 35 centimeter square per second. Okay. So, there are two things that come out of here. The units for diffusion constant is centimeter square per second, and we can calculate, if we know the mobility of the carriers, from the mobility we can calculate what is going to be the diffusion coefficient for carriers. Similarly, we can calculate for holes if we know the mobility. So, this then gives us a relationship between the mobility and diffusion coefficient of the semiconductor. Keep in mind, this whole derivation is for non-degenerate semiconductors. This is for non-degenerate semiconductors. Had it been a degenerate semiconductor, we would have done the Fermi direct integration in using this expression, and that would be slightly different expression. Also, the other important point here is that we have derived this for a equilibrium situation, but this Einstein relationship is equally valid for a non-equilibrium situation. We will not do that derivation here, but this expression is equally applicable to a non-equilibrium situation. So, now we have a relationship between mu n and d n or mu p or d p, and we can use that for our purpose. So, if we then look at what would be what will happen to d diffusion coefficient of electron or holes, if we look at what will happen to it if I change the doping concentration. So, the doping concentration goes from 10 to the power 14 per centimeter cube to something like 10 to the power 19 per centimeter cube, how will my diffusion coefficient change? Whether it is donor or acceptor, how will it change? How would we find that expression? Here we are going to use the Einstein relationship, which basically says that mu n, if I am talking about electrons, divided by d n for a non-degenerate semiconductor is a constant. Basically, it says then that whatever expression we found, whatever relationship between we found for the mobility of carriers and doping concentration, the same behavior will be seen for diffusion constant. So, let me remind you what we saw in case of mobility in a schematic form. As we went from low to high concentration, the mobility drops like this. For you can also plot for mu p, which basically means that d n will also follow a similar behavior. Since this is a constant, it will also drop as we go to higher concentration. Now, this is of course physically also makes sense, because the diffusion coefficient is due to the thermal motion of particles, and mobility is also due to thermal motion. In addition to that, you have response to electric field, but scattering events are there in both of them. And this drop in the mobility is because as we increase the doping concentration and A and D, as we increase the doping concentration, you have more impurity scattering as opposed to the lattice scattering, and hence you have drop in the mobility, and the same phenomena is true for diffusion coefficient. If we try to see the same behavior for different concentration, what will happen to the diffusion constant of n as a function of temperature? Schematically, what we expect is that it will be the similar behavior. If I plot temperature, range of -50 to 200, the mobility for low doping concentration sees on the log scale, on the log scale, drops as the temperature increases, because as the temperature increases, you have more and more of lattice scattering taking place, and the mobility drops fast, and this is for light doping. But if I increase the doping concentration, then the same dependence might be more flat, and this is for heavy doping, approximately 10 to the power 19. Let me say schematically trying to plot the mobility. The reason for this more flat dependence is because at higher concentration, what we have is more of a impurity scattering that is dominating over the lattice scattering, and hence the behavior is more flat. So, this is basically the behavior as a function of temperature for diffusion constant, which is also looks similar to for the mobility constant. So, this is for the diffusion constant depending on how much doping I have in the semiconductor. this tells me what my diffusion constant is, it tells me how it will behave if I change doping concentration, and it also tells me how it will behave if I change the temperature for a light doping semiconductor or a heavily doped semiconductor. It is going to basically follow similar behavior as of the mobility of the respective carrier. Now, proceeding further, let us take an example of where diffusion is going to be important before we go further. So, examples, one example we have already seen that diffusion is going to be important when you have non-uniform doping in the material. Then the diffusion will take place. Diffusion will be important when you have two different materials adjacent to each other. Material in close contact, and we will see an example of that when we look at p-n junctions. One can have the same situation when we have a metal semiconductor contact, then also there will be a diffusion process between the two different materials. There are other ways in which you can have concentration gradient, and that is by carrier injection across a device, carrier injection. In the device, and that will lead to non-uniform carrier concentration, and diffusion will become important. One can have a photo generation of carriers. And that would also lead to non-uniform carrier concentration. So, we will see later that diffusion is an extremely important process in deciding the device behavior in many of these devices. So, to take a numerical example, let us take a semiconductor. So, I am going to take a semiconductor which has donor concentration which is being represented by an exponential equation. So, donor concentration here is being given by the concentration at the surface, let us say N0, and then it is reducing exponentially. This is the behavior in a semiconductor. What we want to find out is what will be the electric field, what is the electric field inside the material because of this non-uniform doping of the material. Now, from in the equilibrium equation as we derived for earlier, we can situation would be where drift of the carriers is going to be equal to diffusion of the carriers. This would be the equilibrium situation, and I am interested in finding out the electric field. So, electric field is going to be nothing but d n over mu n d n dx over n with a negative sign. Since I know n, I know I do not know n, I know n of d, and if n of d is much greater than the intrinsic carrier concentration, then I can assume that n of d is equal to n for complete ionization. In that situation, I can write the electric field is going to be g n over mu n, the differentiation of this equation converted to the carrier concentration divided by n, and that will lead to n naught exponential n is nothing but this expression itself, and hence I have the expression for electric field, which is saying electric field is going to be this coefficient multiplied by lambda, and this will become positive. So, and I know dn mu divided by mu n is a constant, which is given by lambda. D by mu is k T over q. So, this is the expression we get. We get that if I have an exponential distribution of carriers in the semiconductor, I will get a constant electric field inside the semiconductor. And so, if I plot the electric field inside the semiconductor, I will get in equilibrium the band structure will be Fermi level being constant, and since electric field is given by 1 over q the band bending, which is constant, this means that the bands are straight in this structure E c E v, and this is leading to a electric field E, which is constant. So, in this example of equilibrium field developed in the semiconductor, we had a non-uniform concentration of dopant, and that led to a constant electric field in the semiconductor. And so, now to summarize, we in addition to drift and generation recombination, we have another process for transport of semiconductors, which is basically diffusion, and we can account for diffusion of carriers, and the current generated because of diffusion can be given. The current density for holes is given by the expression Q, diffusion coefficient dP dx. Similarly, we derived that and we wrote the expression for the electrons, that will be given by Q dN dx. And then we further found out that diffusion constant for any of the carriers mu n, or maybe I should write it in the general form, mu over d is given by q over k T. This is for a non-degenerate semiconductor. So, this is the Einstein relationship, and it holds for non-equilibrium situation also. So, it is applicable for non-equilibrium, although we derived it for the equilibrium situation. So, now we have at the end of this lecture, we have our expression for drift, that is response of carriers to the electric field. We wrote the expression for J p and J n for that. We have expression for current density due to diffusion. We know the rate at which the carriers will be generated or recombined. Adding all these processes, then we would like to write an expression for all the responses of carriers to these fields, and equation that will help us solve the device characteristics. That we will do in the next lecture.